December 2019, China reported the first emergence of a virus spreading in Wuhan in Hubei province. In a matter of weeks, cases of the novel coronavirus began to pop up across China and eventually the globe at an exponential rate. Since that time, there have been over 7 million official cases across the world. The coronavirus is named for the surface spikes on it that give the appearance of a crown. COVID-19 refers to the disease caused by SARS-CoV-2, just as AIDS is the disease caused by the virus HIV. Although there are hundreds of coronaviruses across the world, only 7 have been shown to cause disease in humans. They repeatedly jump from one species to another as they acquire key mutations in their RNA that allow them to infect new hosts time and again. To infect lung cells, SARS-CoV-2 needs to bind to a particular receptor called ACE2. The spike proteins on the virus have evolved to bind tightly to ACE2 and then to get into the cells, sort of like a lock and key. The instructions for this spike protein are encoded in the SARS-CoV-2 RNA genome, which is essentially a messenger RNA that can be directly translated into a protein. After it is made, the large protein is then chopped up into smaller functional proteins by the main protease Mpro. Some of these smaller functional proteins assemble to either make spike proteins or RNA-dependent RNA polymerase, for short RDRP, which copy the viral RNA. Currently, scientists are trying to find drugs that can either block Mpro from chopping up the main protein into smaller functional proteins, or drugs that can block RDRP from copying the viral RNA. However, vaccine design targets the external spike protein. A safe and effective vaccine will stimulate our immune systems to make antibodies that can bind to and neutralize the spike protein without the coronavirus ever getting into the cell. Determining protein structure is vital to our approach to drug design and a better understanding of SARS-CoV-2. Scientists have 2 ways for doing so: cryo-electron microscopy and X-ray crystallography. With X-ray crystallography, scientists grow crystals of pure protein and decipher their structure by bombarding them with X-rays from a high-energy electron beam. With cryo-electron microscopy, scientists cool the proteins so they almost stop moving and use an electron microscope to visualize their structure. Either process can take up to months if you're dealing with a new protein, but since this virus is similar to the original SARS virus, it should be easier to determine which existing viral inhibitors might block these proteins.